Welcome to this video from the G.EN.ESI project. This video presents the different functionality of the inter-operable and integrated software platform developed in the G.EN.ESI project. The G.EN.ESI project aims to support the integration of eco-design within design and development process by developing a methodology and an interoperable software platform. The G.EN.ESI methodology is a structured workflow for introducing environmental consideration into an existing product development process, and the G.EN.ESI platform is a set of interoperable CAD-integrated software tools that help assess and address the environmental impacts of products you are designing. This research project started in 2012 and involves 8 partners, 3 from academia, the University of Bath, the University Politecnica del Marche, and Grenoble INP. 1 public institution, ENEA, National Agency for New Technology, Energy and Sustainable Economic Development, and 4 industrial partners, Granta Design, Cyber Environment, Faber, and Bungli Fiori Vectron. It is co-financed by the European Commission. The G.EN.ESI platform is a suite of 8 tools. The 2 first ones are the CAD and PLM gateway. They are the interface with the CAD software system. The web interface, which is a way of using the information from the BOM file without having a CAD system, DFEE, Design for Energy Efficiency, Lean DFD, Lean Design for Disassembly, Everde, which is a lifecycle assessment facility, and CBR, the case-based reasoning tools. If you look at the platform architecture, we can see that all the tools have a connection to one another through the XML BOM file and the corporate database. We are going to start this demonstration with the use of the Granta Eco-Design platform to perform a first environmental analysis of the product using the CAD software Creo.
The Granta Eco-Design platform environments are a suite of tools organized around a data management system hosted in G.EN.ESI. This system can host external reference databases such as Material Universe, MMPDS, Campus, and many more, as well as company proprietary data. This data can be exploited using MI Material Gateway embedded in CAD and PLM software for first environmental assessment. A web-based tool called MI BOM Analyzer can be used to perform the same type of analysis without access to CAD software. When engineers need accurate material property data, including eco-properties for product design analysis and simulation, G.EN.ESI Material Gateway provides direct access to apply this vital data quickly and traceably within design software. Today we're going to start from a cooker hood CAD drawing where materials, processes, product transferred, and use assignments have already been entered. Opening the MI Material Gateway for Creo, we can see a drop-down list of the cooker hood parts and the associated materials processes assigned to each one. By clicking on a specific part, we highlight it on the drawing. Information about transport and use can be seen in the View and Edit Transport and Use page. We can associate to the product a distance for transport in kilometers or miles and the transport type. Here we have entered 1000 kilometers per truck. In the use section, it is possible to indicate if the product will be using energy in order to compute its impact in use. Depending on the energy conversion, the page proposes different properties to populate. In the cooker hood case, we can indicate the product life cycle in years and the energy conversion. The energy conversion is electric to mechanical due to the presence of an electrical motor of the product defined here by its power rating, usage in days per year, and in hours per day. We can also define the product as mobile or not, and additional properties are proposed if the mobile is selected. Our product is not mobile, so the mobile mode is not selected. Based on the information provided for the product, a quick eco-impact assessment can be done directly from MI Gateway. We can go in the dashboard area and select the Eco Audit tool from the drop-down list. Two versions exist for data visualization, a detailed version and a summary version. In the summary version, we have an estimate of the energy usage, the CO2 footprint, water usage, and price. Each icon shows more details about how these values were obtained. For this particular case, we have a current total of 7,500 megajoules for energy consumption, 420 kilograms of CO2, and 4,700 liters of water. We set as a baseline the current design in order to compare this to the new design we will shortly create. This is done by clicking on the Set Baseline button. One of the ways to change our design to try to improve our eco-indicators results is to change the material and process assignments. There are several ways to do this operation. We can right-click, select Find Alternatives, and then browse for the desired material. We can right-click and select the materials from favorites if it has been previously added. Or we can add the materials by searching for certain properties that meet certain requirements. An easy way to assign a material is to copy the assignment and paste it and confirm. By updating the Eco Audit dashboard, we observe a decrease in energy usage, a reduction of CO2 footprint, and of water usage. By just a couple of clicks, we can have an idea of the ecological impact of our product and can easily explore alternatives to improve it. When the CAD engineer finds a new design they would like to explore in more details, they can run an Eco Audit comparison report that will be saved into a PDF file that can be shared with decision makers. The biggest impact of this product is due to the energy usage with a gain of 10%. Again, we can see the analysis for the comparison baseline and the new concept. The report will contain the ecological impact comparison between the two designs tested so that the baseline and the new concept can be analyzed. The report covers the energy usage, CO2 footprint, water usage, cost summary, and end-of-life summary. Looking at the energy usage summary, we can see that the reduction is generated mostly by use, followed by material selection, which can be later recovered at the end of life when the material is recycled. The effects of manufacture, transport, and disposal of energy usage are too low to appear on the chart, but their impact can be found in the table presented beneath. Further down, a similar impact can be found for the CO2 footprint, while for water usage, material selection is the dominant factor when assessing the eco-impact. Going back to the View and Edit Assignments tab, we can export assignments to an XML file that can be later opened into third-party tools. An example of this functionality will be explored using the MI BOM analyzer. If the user doesn't have access to a CAD software but is interested to run this analysis, they can use the MI BOM analyzer. This is a tool used for life cycle interpretation, which in just a few clicks can assess the impact of the material or process change to energy usage, CO2, footprint, water usage, and costs. We open the XML file created in the previous steps and see the table of assignments mainly in the CAD software via Material Gateway. If some materials or process assignments were missing in the previous steps, they can be completed in this tool. In addition, it is possible to assign predefined parts to the bill of material. For this particular case, we can see lamps and motors. This can be assigned to the part of the drawing that they're supposed to host the lamp and the motor. Inside each part, we have details of the different aspects as efficiency versus power of the motor, or the luminescence and the power of the lamp. We assign the lamp and motor by adding a new part to the component and then drag and drop the specific part into place. Two LED lamps are assigned to our component as well as a motor part. As demonstrated in MI Material Gateway, it is possible to give information about transport and use. Once the assignments are made, a report can be generated by going to the Reports tab and clicking on the desired report. The report is a PDF file similar to the one generated within the MI Material Gateway. The report covers the energy usage, CO2 footprint, water usage, and end-of-life summary, as well as how to improve this analysis section, where data imported from other tools of the G.EN.ESI platform is presented. Any additional information derived from the platform tools will be stored in this section. It is possible to save this project into an XML format to reuse it later or upload it into other tools of the G.EN.ESI platform. The MI Material Gateway plugin is also available within the PLM software. In this example, we will show it working in Team Center. It has the same capabilities as the plugin for CAD software, including material assignment, processes, transport and use, and end of life. Here we are searching for a new material and assigning it to the plugin. It is then possible to create an eco-audit report, just as within the CAD software.
So once you've generated the BOM file, you can actually start using 3 different tools which will help you improve certain aspects of product lifecycle. So what you're saying right now is Lean DFT, Lean Design for Disassembly. You can also use the XML BOM file in DFEE, which is a tool aimed at providing an evaluation of energy efficiency of your product, or use it in CBR, which will give you advice and guidelines on how to improve your product. So Lean DFD has 2 main models: the disassembly analysis or the end-of-life analysis. So we're going to start with the disassembly analysis. In this interface, you will choose which component you want to remove and disassemble from your product. So in this case, we're going to disassemble this component, which is the motor, and this component, which is the electronic board of the product. Once you've selected the components you wish to add, you then define the precedencies of them. So a precedency is all the components you have to extract before extracting the targeted components. So at the 0 level, you have all the components that you can access from the outside. The second level would be the product you can access once you remove the first level, and so on and so on. So in the case of the product we're showing right now, you can access one of the targeted components at level 3, meaning that you need 3 disassembly operations to extract it. And the last one, you need 4 operations of disassembly to extract it. Once you've decomposed your product, all the precedences in your product, you have to identify and define how the different parts are tied together. Based on the level, on the different level and the composition of your product, you or I have here all the constrained components, meaning all the components you need to disassemble to access the target one. So for each component, you're supposed to identify to which component it is linked and what type of liaison you have. So for example, this part is assembled with this part using 8 screws. You have different type of liaison, you have screw, you have snap fit, you have electrical plug, and with each liaison and each level of disassembly, you can actually evaluate a disassembly sequence which will provide you with the time and the cost of disassembling different parts of your product. In the last part of the software, you can choose the component you wish to evaluate this disassembly performance. So for example, in this case, we're going to have a look at the electrical board of the product we're seeing right now. So you have 2 ways to disassemble your product, and they both take they both needed 44.1 seconds to be disassembled for a cost of 0.25 euro. So as you can see, the first operation is timeless because it's actually just removing the filter, which doesn't take long because they have no liaison in between those components. But then you have to unscrew this part and to unscrew this and to unclip this part, which take a little less longer than unscrewing the part, and so on and so on. So for the entire disassembly sequence, you will need 44.1 seconds. As you can see here, you can see both those components are on level 0 of the product disassembly tree. This component is level 1, this component is level 2, this component is level 3, and this component is level 4. If we look at the other part we wish to disassemble, the scores are a little bit different. Even though there's less operation to access, even though the motor is at level 3, so here disassembling the motor will cost more and will need more time to be completely disassembled. So this is the type of information you can have from the first part of LINDFD. The second part of LINDFD is the end-of-life analysis. Here you will evaluate the performance in terms of recyclability, hazardous waste, and all the different information you need regarding the end-of-life. So in this case, you will have information on the amount of hazardous mass based on the material property of your product, what is biodegradable in your product and what is incinerable. Here you have the type of plastic parts that are incompatible with one another. So for example, you have ABS and PVC, which are actually not compatible in terms of recycling. If we look at the recyclability index, here you can define which components, if some components have impurity or contaminating material in them. So here you have a list of different iron parts which have been linked with zinc alloy, which means that they would be less recyclable than if they were completely pure. And then the recyclability index of your entire product, which is for the cooker hood almost 80%. This is the type of information you have in LINDFD. Like LINDFD, DFEE is a tool that will help you evaluate the performance of your product on a specific problematic that is important for all electromechanical products, which is the use phase and the energy efficiency during use phase. Like every G.EN.ESI tool, you can use the XML BOM files that's been generated in the MI gateway to CAD. You can also use a CAD file, like in LINDFD. In this case, information have already been filled in on the energy performance of the product, which is, once again, a cooker hood. So here you can see that the energy consumption of the product is due, half of it is due to the consumption of the electric motor, and a little part of it, and the rest is due to the energy consumption of the halogen lamp of the cooker hood. How we define this performance? So for example, if I click on the component, which is the lamp, I can define is its use profile. In our case, for example, right now, the component type is a lamp. We can decide to change the halogen lamp by a LED one, which is more energy efficient. In this case, the database of DFEE gives us the information on the power consumed by this type of components. So it's 4 watts. If we look at the user profile now, we have to define for how long it is used. So the use scenario of this product tells us that it's used all year long for 2 hours. So I've said that it has been used every day for 365 days a week and for 2 hours a day. So here you can see the total energy consumption of the lamp. If we go back to the product profile, you can see that we drastically reduce the environmental impact, the energy consumption of the product, and that means also the environmental impact for this type of product. Here we have defined the lifetime of the product, the country of use, which will influence the energy mix that we use for calculation of carbon footprint and costs. If we look at the motor now, we can see that we define different working points. In this case, we have defined 3 working points, which have different efficiency and different power consumption over the lifetime. This can help you when you have product like a fan, for example, which is used at different efficiency, with different speed, so meaning with different energy consumption level. In LeanDFD, like in other tools, you can or export the file as an XML BOM file.
It can be uploaded once again in the web BOM analyzer, and the generated report will include this additional data.
So CBR is a tool that's going to help you improve your product once you've identified the most problematic part of it regarding its environmental performance. So as all the tools, you can open the XML BOM file to have an idea of the structure of your product. So for example, once again here we have the cooker hood. CBR will help you select the most appropriate guideline that you can apply to your product in order to improve it. For example, we know that energy consumption of the lamp is quite problematic for this type of product. So you select the lamp, you select the product family, which is a cooker hood. You double click on the part, and then you can define what this functional group is. So for example, this is a lamp, and the standard component associated with it is also a lamp. If I search into the database of components, you can see that you have 12 guidelines that can help you improve your product environmental performance. If you decide to apply some of them on your product and you wish to know which one, you can click on them. That means that you're going to select them and associate them to the part of your product. Once you've done that, you can save your project in the CBR format. That means that you will have access in the future to the decision you made regarding which guideline you applied and to which part of your product. If we look at other type of functional group, like the motor, for example, which was also a big contributor to the environmental impact, you can see that you have 7 guidelines, which is a little less than the number we had for the lamp. This database can be improved, can be customized within the company in the expert interface. You only have access right now to the non-expert interface. If you don't want to associate anything with your project, you can go into the browse mode, where you will have access to the list of guidelines and the list of previous projects you've saved in the CBR format. Here you have access to the entire list of guidelines, which today is 53 guidelines that have been classified into product family, functional group, standard component, objective, lifecycle phases. So for example, you can select the objective you want to reach with your product. For example, increase use efficiency, independently from the product family, the functional group, or the standard component. Here you can see that you have 9 guidelines and can help you increase use efficiency during product design. So CBR would be your tool of choice when you don't know how to improve your product environmental performance and you wish to have more information on which type of modification of your product design you can make to improve it in terms of ecological impact. If you wish now to have more detailed environmental analysis of your product performances, you can use the Everyday tool. Like the eco-audit report from the MI Gateway, you can assess the environmental impact of your product lifecycle using Everyday. You can see here that you can import the BOM file with the format of the G.EN.ESI project. Once you've imported your file, you can see your file in Modify Study variant. If I click on this, I can see that I've imported 3 different files. If I look at the second one, I'm going to have access to all the information that was in the BOM file in the different lifecycle phases of the product. For example, all the material composition of the components of the product are going to be stored in the components category of the pre-manufacturing phase. If I click on components, I'm going to have access to the full list of components that I have in my BOM file. If I click, for example, on lamp, I can see that I have an electrical appliance of the family lighting and lamps, which is an halogen lamp. So this list will represent the composition in terms of material of your product life cycle that is stored in the BOM file of your product. The manufacturing processes that you've added to each of your parts will be available in this phase, the manufacturing processes detail of the manufacturing phase. And the information you've uploaded in the FEE regarding energy consumption of your product are going to be stored in the product use phase and under the heading energy consumption. Here you can see that you have 3 energy consumption types. Energy consumption of both halogen lamps and the energy consumption of the induction motor. In Everyday, you have a detailed description card which can help you identify different details of your life cycle assessment. For example, here we've added the functional unit for the cooker hood, which is draw air for the cooking area with a suction rate of 660 meter cube hours for 2 hours a day for a lifetime of 9 years. This information is not available in the BOM file, but you can add it in Everyday. So once you're satisfied with the definition of your product lifecycle inventory, you can evaluate the result of the lifecycle impact assessment. So in here you will find on all the environmental analysis you've been storing into your profile. So here you have the value of the 11 indicators we have in Everyday. If we click on percentage value, we can see now that most of the contribution happened during pre-manufacturing phase or during use and end of life. This is in line with what we found in Material Gateway. So for example, we can see that the consumption of material resources happened during pre-manufacturing phase, and this is due to the fact that all consumption of resources for material extraction has been accounted for in the pre-manufacturing phase of the cooker hood. If we look now at two indicators that reflect the energy consumption, we can see here that it's a use phase and end of life that's contributing the most to the environmental impact of the product. We can see the same for the climate change evaluation. In addition to the evaluation, you can do a significance test and a completeness check to be sure that the results you have are robust enough for you to make a decision based upon them. Another way to evaluate your study is to compare two different designs of the same product. So you can compare two products with the same functional unit, in this case, a first version of the cooker hood and a second updated version of it. In this case, the target plot diagram gives you information on where your product has improved its environmental performance and where it has not. So we can see here that, for example, the consumption of material resources is largely the same as the one before. But if we look now at consumption of non-renewable energy, and climate change, being EN number 5, 6, and 7, we can see that the emissions have been reduced drastically. So Everdy is your tool of choice when you have defined your inventory completely. You have a complete BOM file with a good level of detail, and you want to check on more indicators than the one you have access to in AMI Material Gateway, and be sure that you're making the right decision based on 11 indicators. Here is an overview of all the data you can find in the different tools of the platform. You have an initial environmental assessment on energy, CO2 and water of your product life cycle, thanks to the AMI Material Gateway to CAD and PLM. This provides you early on in the design process with information on environmental performance of your product. You'll have then access to a detailed analysis of energy consumption in use phase and end of life, including the disassemblability of your product in DFEE and Lean DFD. Everdy provides you with a more detailed environmental assessment at the end of your design project that you can use for setting new targets for your next design project. If you want to find out more about the platform and the G.EN.ESI tool, you can check out the G.EN.ESI website. You will also find information on the G.EN.ESI methodology and the training material on eco-design we have available.